So, in our last class we were discussing about the interprocess communication primitives like message passing, then shared memory, then we have got these pipes and all. So, before proceeding further, so we would like to highlight like how the program will look like when it is loaded into the main memory. So, here we have got a sample C code where we see that there we have got some of the global variables like x and y, and between x and y. So, x is uninitialized whereas y is initialized to 15, and we have got a main program where some parameter arguments have been passed argc and cat star argv. So, the argc and argv, so these two parameters are passed, and within the main program. So, we have got this local variables values and I. Out of these values is an integer pointer and I is an integer. And in the code we have got this we first do a malloc operation. So, it calls malloc, and in this malloc it returns size of integer into 5. So, it returns space for 5 integers, and then that return pointer is stored into the values variable. And then in a for loop, so we are initializing the value we are initializing these values to I. So, values I equal to I. So, this is initializing the values variable to some values, okay, and then return 0. Now, our objective is not to understand the meaning of this program, rather we would like to see how this program will look like when it is loaded into the main memory. So, as we know that any program that is loaded, so it can be considered to be consisting of 3 segments at least: the code segment, the data segment and the stack segment. So, this we have discussed previously. Now, how do they look like? So, if you look into this layout, so if it is loaded, if the program is loaded from this address going towards the highest memory address like this. So, if it is the program is loaded in this region, then in the lower part of this memory locations, the text of the program will be loaded. So, this program when it passes through a compiler, so it will generate some machine code, and that machine code will be loaded, will be copied into this text region. However, we need to create. So, this is basically the portion corresponding to this part. Okay. So, values equal to this. So, what are the operations to be done when this program starts executing? As you know that when a C program starts executing, the control is transferred to the first executable statement of the function main, and this happens to be the first executable statement of main. So, this is the control will be transferred here. Now, apart from that, for the variables we need some space where the variables will be residing in the main memory, and then we have got this these global variables x and y. So, they are kept in the data segment. So, this whole part is the data segment, and whereas the previous portion that we have. So, this part, so this corresponds to the code segment. So, we have got code segment and data segment, and data segment is further divided into 2 parts. In one part of it we keep uninitialized data, and in the other part we keep initialized data. So, uninitialized data like x, it will go to uninitialized data because it is not initialized, and the initialized data. So, this will be y will be assigned some space here. So, what will be the size of this data segment? That depends on the number of global variables you have and their types, size requirements, etc. And again the size of this initialized data and uninitialized data segment. So, that will also depend on the variables that you have. So, some system may put a limit on the size of these segments, whereas some segments some other operating systems they may not put any limit. So, it varies from system to system. Then after that we have to see for the functions, like within the main is a function, and within that we have got these 2 local variables values and I. So, they are assigned to the stack segment, and as I said that data and this heap and stack. So, they are allocated on the same portion of memory, but they grow in the opposite direction. So, this entire chunk of memory space, so this is allocated to stack plus heap. They are allocated to stack plus heap. So, stack starts growing from the highest address, heap starts growing from the lowest address. So, they grow in the opposite direction. so that if a program makes use of more of stack space, then it will be able to do that. On the other hand, if a program does less of function calls, but more of dynamic allocation, so they will be done, they will be allocated the heap space. So, they are put on the opposite ends of the same memory block, and they grow like that, the stack and heap. So, in this case you see that this main program, it has got this local variables values and I. So, they are assigned space into this stack segment, whereas this when this particular function is called, this malloc function is called. So, what the system does, it tries to assign some dynamic space to the program. Okay. So, here I am asking for space which is equal to 5 integers. So, if I have got space available in this stack plus heap segment, what the system will do, it will allocate 5 memory locations. So, if I say that these are those 5 memory locations. So, these 5 memory locations will be allocated, and that pointer will be given to this values variable, and then so that is allocated in the heap. So, the stack and heap, they grow in the opposite direction. So, they are so it is allocated here. Now, if a program is doing is a recursive program, then what will happen? So, it will have more lot of function called recursive calls. So, the stack segment will grow significantly. On the other hand, if a program has got more of this dynamic storage utilization, like linked list type of program, so they for them this heap segment will grow significantly. So, whatever it is, ultimately we have got this variables implemented, and then this argc argv. So, they are actually some parameters for the whole program, and they are allocated some space which is over and above the original space, because it is coming from some other program. So, whichever program is calling this, so they will be giving this argc argv. Sometimes so this also this is also local variable, this parameters that is passed for the main routine. So, you can say that actually this is also a part of this stack for this for the function main. So, I should start this stack plus this thing from here to include that argc and argv. So, they are parameters. So, they are also created onto the stack. So, if you are familiar with compiler design courses, so you will know that there is something called activation record. So, when a procedure is called, so it creates the system creates some activation record, and this activation record, so this holds the information like the parameters that are passed, the local variables that are created, and all that. And whenever if a call is made, one such activation record is pushed into the stack. So, you can say that this argc argv values and I, so they will constitute one activation record for the function main. So, that will be put into the stack, and the system will go, and the execution will start like that. And when this main is over, this whole thing will be popped out from this stack. So, it will go out, and then the stack content will become similar as the previous one from which point it was called. So, I would suggest that you look into some compiler design books for details about this activation record and all, and you will get a better idea like how these variables are assigned. So, as an operating system designer, we have to provide a mechanism by which this compiler designer can create this activation record, put them onto stack, etc. So, that is the duty of the OS designer. So, with this we come to a conclusion of this discussion on process. A process is a program under execution. So, a program is I should say that it is a static item that is residing in the disk, and then when it goes to goes into execution, so it becomes a process. Each process has got a process control block that holds all the information regarding the process, starting with the identification of the process, its ownership and all, up to the context that is required, like the CPU register values, then this program counter, then this memory limits, then this scheduling related parameters like your timing, the CPU usage, disk usage, memory usage. So, like that. Now, process we have seen that process goes through various states in its execution. When it is when the user has just given the command to execute a program, So, that creates a new process. So, the state of the process is new. After the program has been loaded into main memory or the process has been loaded into main memory. So, it is ready. So, it is ready in the sense that if it gets CPU, now it can start executing. So, after some time the scheduler will pick up the process for execution. So, it goes to the running state, and during running. So, there can be two situations, after some time maybe the process wants to need some IO operation, or the process may have to wait for some event, like a process might have created a child process and this process now wants to wait for the child to be over. So, that way the process may be put into a blocked state waiting for some input output operation or some event. Or maybe that the process is given CPU for a small time quantum. So, after that time quantum expires, the process is taken back from the running state and it is put back into the ready state. So, another process gets chance for execution. So, this way a process from the running state, it can go to a waiting state or it can go to a blocked state. And also a process while executing in the CPU, it may terminate because its execution is over. So, it goes to a state which is called terminated, and we remember this because the parent process who created this one may need to know what was the outcome of the previous process that it created. So, it may be interested about the successful termination of the process and all. So, this the exit code of the process becomes important. So, we have seen that the ready queue, it contains all ready processes waiting for getting the CPU. A parent process may create several children processes. So, that way there is a parent child relationship between the processes, and of course, processes need synchronization and communication. This is very important because a process, a number of processes, they may constitute a whole system, and as a result we will be requiring them to communicate between themselves, and sometimes different parts of computation is done by different processes. So, we need to have proper synchronization between them. So, in our successive classes, so we will be looking into this synchronization, so then this scheduling, so etcetera in more detail. So, with that we end this portion, and so next we will be going to another topic where we will be discussing about the something called threads. Okay. So, this threads is basically a thread is. So, next we will be going to this discussion on threads. So, basically it is a variant of process. We will see that okay, it is not as much detailed as process. So, what happens is that many a times the computation that we are doing across different processes, they are quite similar. For example, like if we are doing say web browsing. So, web browsing ultimately it is contacting some server, and maybe there are 10 different people who are accessing from different places, and all of them are trying to access a server. So, as far as the server is concerned, so it is getting request from 10 different clients and it is trying to process them. So, one way for handling this type of situation is that you create you serve these client requests one by one, but that way somebody may feel that okay, I am not getting enough care or enough attention. So, response to some of the client requests may be slow. So, we want to make it fast, and for making it fast, what we have to do is that we have to create multiple processes. Okay. So, each client request comes, so we create a process, and that process takes care of that particular request. Now, the difficulty with this type of situation is that whenever we have got a process, means we have got this code, data and stack segments, but that often becomes too heavy, and we will see that in different applications. So, that much distinction between these processes is not necessary. So, in this part of the lecture, so we will be looking into a new concept called threads, which will make this execution much more simple, and that will help us in developing programs, particularly for multi-core environments where there several cores are there and they can take up the different jobs. So, overall what the topics that we are going to cover is, first we will have an overview of what is threads, etc. We will be talking about multi-core programming, then we will talk about multi-threading model. So, multi-core, I hope you are now familiar, like most of these CPU chips that you get. So, they have got multiple cores in them. Now, it is not sufficient that a processor chip, it has got say 8 different cores. What is required is that as an OS designer, I should be able to put 8 different operations onto those 8 different cores. So, if I am not able to do that, so if if my OS cannot create 8 different parallel tasks and put them onto these 8 cores, then ultimately it becomes a sequential one. So, performance wise we do not see any difference. So, it is not only the availability of the hardware. So, it is the operating system's responsibility to exploit that hardware in a proper fashion. So, this threading concept will help us in doing that exploitation. So, we will be talking about multi-threading model. So, there can be different types of models for these multiple threads, like how they are related to each other. So, we will be looking into that. Now, for making this thread based programming easy, so there are several thread libraries that are available. So, we will be looking into some of them, though not in much detail, but we will see we will have a glimpse of like how the thread libraries will look like and what are the essential features that we will get from a thread library. So, that if you are exploring a particular library, you can look into those features and start using them. There are some implicit threading, like automatically the threading occurs, and then we have got some threading issues. So, that we will discuss one after the other. So, why should we go for this threading? Most modern applications are multi-threaded. So, a typical example that I have is that I said previously is like this. So, I have got a web server. So, this is a web server, and to this web server, so we have got several client requests that are coming. So, these client requests, so that are coming, so they are similar in the sense that they are trying to access some information from this web server and get something done. Okay. So, that way they are more or less similar, but maybe this client request is trying to access some part of information, whereas this fellow is trying to access some other part of information, but it is accessing all of them. They are using some services which are provided by the web server. So, if you look into the code that you have here and the code that you have here and the code that you have here. So, there are lots of similarities between them, because ultimately what they are doing is requesting for some service from the web server. Or if you have got a database server, then in the case of database server, the type of operations that we do is to access some of the records that we have in the database and possibly modify them. Now, all these queries that are coming, so all these queries they are again of similar structure, in the sense that what they do is that they are trying to access some records in the database and then trying to do some modification to the database and all. So, that way this structure of all these are quite similar. Now, so that is why it is said that most modern applications are multi-threaded. So, we have got this another example here. After some time we will see, and threads they will run within an application. So, application has got multiple thread and these threads will run in parallel. So, a typical example may be like this, that so one typical example may be like this. So, we have got multiple tasks with applications can be implemented by separate threads, like we may have some application that performs this thing. So, it updates display, fetches data, maybe from file, maybe from internet, wherever it is, then it performs some spell checking and answer a network request. Maybe in one application we are doing these 4 services. Now, these 4 services you see they can go in parallel. So, if you write a single piece of code which is doing all these things, the code becomes very clumsy. So, instead of that we design different codes for different applications. So, that is for different tasks. So, that is one way, but all of them are part of same application. Okay, but their tasks are different. So, as a result what will happen is that if you look into the individual operation that this fellow is doing, so it is different from this, but major part of it, major part of them may be similar also, because they are accessing the same data elements and they are modifying the same data element. So, like that. So, that way so whatever data this fellow has fetched, so this spell checking module, so it is working on that data set. So, if you make it separate, so if you create two different processes, suppose this fetch data is done by P1 and spell check is done by P2. Now, the difficulty that we have seen previously between P1 and P2, even if they are so even if there is a parent child relationship between P1 and P2, so they do not share the data segment between them. So, whatever has been fetched by P1, so for P2 that is not visible. So, for P2 for making it visible to P2, I have to put them on the shared memory, and from there only this P1 and P2 can see them, and this shared memory is limited in size. As you know that any operating system there will be a limited amount of shared memory. So, designing such a system becomes quite complex. So, if we can do something so that whatever the data segment P1 has, so P2 has it common with P1, and whatever modification P1 is doing, so it is visible to P2, and whatever modification P2 is doing is visible to P1. So, like that if it can be designed. So, this is essentially the idea behind this threading. So, we will have separate threads for doing different for separate operations, but there will be lots of sharing between them. So, this is the this actually summarizes the statement that I was trying to make. So, this process creation is heavyweight, because if we why do we say so? Like if you want to create a process, so that means you have to create the code, data and stack segments for that process, code, data and stack and heap. So, they are to be created for this process, and then possibly you have to tell like which code it should execute. So, you have to use some fork system call. After that there should be some exec system call for doing this operation, and this is heavy because you have to update the process table, you have to create the PCB, and all those things are to be done. So, that way it becomes a heavy thing, and difficulty with being heavy is that if you want to switch between the processes, it becomes time consuming. So, overall throughput of the system will be low. On the other hand, this thread will see that they are defined in such a fashion that you do not have much work to do to create a new thread. Okay. So, this is called a lightweight. So, thread creation is lightweight. Okay. So, we will see how is it lightweight. Now, it can simplify code and thus increase the efficiency. Kernels are generally multi-threaded. So, this statement I would like to emphasize, like so as you know that in any operating system, so we can say that it can be divided into two region. One is called the user space, and other is called the kernel space. Now, in the kernel space we have got the important data structures and routines that are useful by the operating system. So, whenever you need some system service, a program, it has to make a system call, and by this system call the program goes from user space to kernel space and starts executing in the kernel mode. For example, when you are doing the computation like x equal to y plus z, etc., this simple arithmetic logic computation. So, this is fine, but as soon as you are telling that I want to do a printf, of something, then you need to access the IO device, and as a result that goes into the kernel space of execution, or whenever you are trying to create a new process, that it goes into the kernel mode of execution. Now, suppose in this kernel I have got only one thread. Okay. So, only one thread is there. So, whichever process wants to get a system service, it will be using this particular thread for doing the operation. So, as a result, if there are multiple processes or multiple users in the system, so whenever they make a system call, so so only one of them will be allowed and others will be blocked. So, this is a very serious problem, because it may so happen that while executing the system call corresponding to one particular user, so there was an error, maybe because of OS or maybe because of this user the way this call is made etcetera, this call may fail and many things can happen. So, we just take take into consideration the situation that we have got a single thread here in the kernel space, and all the user processes that wants to make system call will be utilizing this particular thread. So, that type of design is known as single threaded kernel. So, this type of design is known as single threaded kernel. Now, initial operating systems that were designed, so they were of this nature, single threaded kernel. The advantage that you get is that, so since there is only one thread inside the kernel, so many problems of this synchronization and inconsistency they get resolved. Okay. So, but but the difficulty that we face with the single threaded kernel is that we cannot get multiple jobs going on simultaneously. So, it may so happen that one user is trying to modify say one user is making a fork system call, by that user wants to create a new process, another program. So, it is trying to do a printf by accessing the printer data, the printer resource. So, that way, so these two as such there is no harm in making them to proceed simultaneously, but since only one thread is available, only one of the processes will be allowed to proceed. So, other one will be blocked till this fellow has finished. So, that way performance the system throughput will be low, but the point is that if we allow multiple threads, then the difficulty that we get is, suppose I have got a process P 1 which is executing a fork, I have got a process P 2 which is also executing a fork. Now, whenever this is done, so if I allow both P 1 and P 2 to come into kernel mode and start executing, then both of them as a part of executing this fork, so they will try to access something called the process table. Okay. So, they will try to access the process table, and this process table updation, it may so happen that this updation becomes inconsistent. Maybe something is written by process 1 and that is overwritten by process 2. This will be more clear when we go to this concurrency control chapter, but whenever you have got any shared resource and multiple processes are trying to modify them, that creates a difficulty. Okay. So, we should allow only one process at a time, but the single threaded kernel, so it has got the advantage because only one process will be allowed or only one thread will be allowed inside the kernel. So, the synchronization problems are solved, but this the throughput or performance will be poor. The multi-threaded kernel, multiple threads can be there inside the kernel mode. So, your throughput or performance will be better, but this design will become more complex because you have to have some protection. So, somehow if there are say many such shared resources, so I should somehow ensure that this process table is not accessed by more than one process simultaneously or more than one thread simultaneously. Similarly, if there is another table which is say the file table that remembers all the open files that we have in the system. So, if two processes they are trying to open files, so they should not be allowed simultaneously to modify this file table. So, that is we should have protection there. So, we should have protection around each of these individual data structures or individual tables. So, that makes it difficult, and with the multi-threaded kernel design, so this is taken care of, and most of the operating systems that we have today, so they are having multi-threaded kernel. So, we will look into this multi-threaded kernel situation in more detail and how the mapping is done between user level and kernel level in case of threading. So, in the successive classes we will see.